Hello friends, in this video today we are going to discuss about Poynting theorem and Poynting vector. Okay, so before we start, please do subscribe the channel, also hit the thumbs up button and share with your friends and inspire me to create new contents for you. So now let's start. First, you say let me write the statement what is Poynting theorem. Poynting theorem, according to this theorem, it states that let me write that Poynting theorem states that the decrease of electromagnetic energy, the decrease of electromagnetic energy per unit time in a certain volume is equal to the rate of doing work plus the flux flows outwards, per unit time. So mathematically we can write this way: minus del t integration v half epsilon naught e plus half mu naught h square. So here it's supposed to be e square, right? And d tau, which is volume element, surface integral e cross h ds, this is area vector, plus integration, this is volume integration, e dot j d tau, right? So here you see, so this is the mathematical expression. Okay, so now I'm going to show you how to obtain this relation. Okay, here this e cross h, this is nothing but Poynting vector. This is Poynting vector. Okay, so what does it represent? We're gonna discuss. Okay, so before we prove this, we must know a few things. Those are, here you see, let me take a new slide. Expression for electrostatic energy, static energy. So which is, let me write it this as UE, that is given by half integration, volume integration, right? E dot d, so d tau, this is a volume element, or it can be written this way: half integration v, you can write this way, because this d can be replaced by epsilon naught e, and if you do so, then what you're gonna have, you're gonna get epsilon naught e square d tau. That's what you're gonna have, right? And Similarly, magnetostatic energy is given by, let me write here um. Okay, so that's going to be half integration, volume integration, b dot h d tau, or you can write half volume integration 1 by mu naught 1 by mu naught b square d tau, because this h can be replaced by 1 by mu naught b, right? So hope you have understood this. So you must know these expressions. I have assumed here that these things are known to you. Okay, so here let me write the meaning of the symbols that I have used here. So this E is nothing but electric field, right, and B is magnetic field, or you can say magnetic flux density, and here this is D is nothing but electric displacement, and H is the magnetic field intensity. Right. Now you see, and let me tell you one more thing. You must know the Maxwell equations. So let me take a new slide. Okay. Here you see. So now we are going to prove the Poynting theorem. Okay. So we know the Maxwell equations. So what are the four Maxwell equations we have? And those Maxwell equations are, let me write Maxwell equations. Maxwell's equations are, so first one, del dot E is equal to rho by epsilon naught. This is one, this is the first one. So rho is the charge density, hope you know this. This is charge density. Right, so rho is the charge density. Now second one is del dot B, that is equal to 0, right? This is number 2. And third one is del cross H. You can write this in terms of H as well as B also. Then J vector plus epsilon naught del E by del T. This is suppose equation number 3, and the last one is del cross E minus mu naught del H by del T. This is equation number 4, right? Here J is the current density. This is current density. Okay, J is the current density. So hope you know these things. So now you see, first let us take the equation number 3. First let me take this equation number 3. So let us take the equation number 3, which implies this. Here you see, this was the equation number 3. So if you take the dot product of E with this equation on both sides. Okay, that means E dot equation number 3. If we do that, then what you're gonna have? We're gonna have here E dot this and E dot this. That's what we're gonna have. So if you open the bracket, then you can write this way. So E dot J plus plus epsilon naught E dot plus epsilon naught E dot del E by del T. You can write that way. Let us suppose this is equation number 5. This is suppose equation number 5. Similarly, if you take H dot equation number 4, H dot equation number 4, taking dot product on both sides of equation number 4, then what you're gonna get? So let me copy the equation number 4. So here you see this is equation number 4. If you take the dot product, H dot this and H dot this, so just wait, you can write directly this way, minus this is just wait, you can write here H dot, right, minus mu naught H dot del H by del T. That's what you can write. So this is suppose equation number 6. Okay, now subtract 5 from 6, subtracting equation number 5 from 6. So let me copy these two equations. Just wait, instead of going the next slide, let me do here, just give me a second. Okay, now equation number 6 minus equation number 5. So left hand side minus left hand side. So let me copy the left hand side of equation number 6, which is this one. This is the left hand side of 6 and minus left hand side of 5. So here is the left hand side of equation number 5. Okay, is equal to then right hand side of 6. So this is the right hand side of 6 minus right hand side of this one, equation number 5. Okay, so here is the right hand side of equation number 5. Okay, now if you remove this bracket, then the plus sign between these two terms, this plus sign gonna be minus. Okay, that's what we're gonna have. Now let me copy this last result and let me go to a new slide. I'm gonna paste that step here. Here is the last step we have got. So now you see what we can do here. If we apply, hope you have got the identity in vector. This can be written in this way: del dot E cross is. E cross is. This is an identity of vector product. So that's nothing but H dot del cross E, then minus E dot del cross H. Okay, so hope you know this identity. So you can write, let me write here, since del dot E cross H can be written in this way, that H dot del cross E is equal to, minus E dot del cross H. So that's why, therefore, this above equation can be written this way. Instead of this side, we can write del dot E cross H is equal to, let me write this one. Okay, that's what we have got. So what we have done, we have replaced this one by this part, right? Or you can see in this equation, you have replaced this result by this one. Okay, so hope you have understood this. Now you see what we can do now. Let me take volume integration on both sides. Taking volume integration on both sides. Okay. Just wait. Instead of writing one by one, let me copy the above equation and let me write. Just wait. Okay. So here, if we take volume integration, so d tau is suppose very small volume element, then here we have to write d tau, then is equal to integration volume element. Here we're going to write d tau. Okay, so just give me a second. Integration volume integration. So here just give me a second. Okay, d tau, then again here you see volume integration. Here also we're going to write d tau. That's what we're going to have, taking volume integral on both sides. Okay. Now, what we are going to do in this case, you see h dot h, that's going to be, h square. So, we can write this way that, just give me a second. Let me explain here. You see, h dot h, you can write h square, right? H square, that's what we can do. If you differentiate it, right? If you differentiate this, let me write on this side. Then what you're gonna have? So to differentiate this, use the product rule. Then you're gonna get this plus again. Sorry. Okay. Same thing. So that's what we're gonna get. So these two are same term because we have here dot product, not cross product. So here the order of these terms doesn't matter. You can write this one first as well. Okay. So that's why we can write 2h dot del h by del t. So from here you see del h square by del t, we have got this one. So del h h into del h by del t, it can be written half of del h square by del t. Sorry, that's what we can write. So we can replace this by this quantity. Okay, similarly we can replace this one by half del e square by del t, right? So hope you have understood this. So now let me clean these things. Just wait. So therefore next step, what we can write, integration del dot, let me just copy it down from above equation. Just wait. So this is, and just mu naught integration volume integration. Here we can write half del h square by del t d tau minus volume integration e dot z del t, sorry, this is z vector, del tau, not del t, then minus you can write the epsilon not outside integration v, so it can be written half this term, half del e square by del t d tau. That's how we can write. Now combining these two terms, what we can do, let me copy this last step and let me go to a new slide. Okay, then what you're gonna have, mu naught, sorry, volume integral mu naught half del H by del T minus epsilon naught half del E square by del T d tau. That's what we can write. Okay, so hope you have understood this. Then minus epsilon naught integration V half sorry, not half, sorry, I missed this term. So minus volume integration E dot z d tau. That's what we have got. Now you see, we can write this term this way as well. So taking this differential coefficient common, so we can write this way also, instead of writing this. So we can write this way. Just give me a second. We can write this way. Del T, integration, volume integration, taking half common also, we can write this way. Epsilon naught del H square by del T minus sorry, this is mu naught, not epsilon naught, then epsilon naught del E square by del T by d tau. That's what we have got. Okay, I think I have missed minus sign somewhere. Let me go back to the previous slide. Let me check what I have missed, where I have missed. Okay, this minus sign I have missed here. So there should be a minus sign here. You see, there should be a minus sign. Okay, if that is the case, then this term should be also negative. Okay, and here this term should be also negative. Okay, so this should be also negative, this one is also negative. Okay, and this is also negative, so we can take the minus sign common, then this sign will be positive, right? So hope you have understood this. So actually what here you see, what I have done, I have missed this minus sign. I forgot to put this minus sign here. Okay, so hope you have understood this. So now you see, so now put this minus sign. Okay, and if this term is negative, then on taking minus sign common, this sign will be positive. Okay, this one becomes positive now, right? Hope you have understood this. So now you see, if we rearrange those terms, then we can write this as like this. Sorry. Okay, then plus integration, volume integration, E dot z vector d tau. That's what we can write. Okay, now using Gauss divergence theorem, you can convert this volume integral to surface integral. Okay, so now you can write this way. Just give me a second. Okay, equal to, so if we convert it into surface integral, this surface enclosed is volume V, right? Hope you have understood this. So now here we're gonna have surface integral. Sorry. So this is the area vector. Okay, so hope you have understood this conversion of surface integral, volume integral to surface integral. So here when you convert this, this del sign should not be written. Okay, so this is Gauss divergence theorem, so we supposed to write this one only, plus E dot J d tau. Let me copy this last step and let me go to a new, let me take a new slide here. So here we have used Gauss divergence theorem. We have obtained this surface integral by using Gauss divergence theorem, right? So using Gauss divergence theorem, what we have got, that volume integration divergence dot del dot E cross H d tau is equal to integration, surface integration E cross H dot ds vector, right? We have got this. Okay, we have used here, that's what we have got, right? So this is nothing but this equation. Let me give it equation number. So let me check what I have given the equation number last time. So equation number 6. So now let me take this as equation number 7. This is equation number 7. Okay, this is equation number 7. This equation number 7 represents the Poynting theorem. Represents the Poynting theorem. So here you see the left hand side term on the left hand side, which is nothing but this. Let me write the left hand side. Okay, so here is the left hand side. What does it mean? So this is nothing but decrease of electromagnetic energy, okay, per unit time, or rate of change of electromagnetic energy, rate of change of electromagnetic energy, right? This is a rate of change of electromagnetic energy. Now you see, let me go back to the first slide. Let me show you something. So here you see this electrostatic energy expression is this, right? So just let me copy this. Okay, so this was the electrostatic energy. This is UE, and you see the electromagnetic energy expression was this. This is the expression for electromagnetic energy. Here you can see half integration, this one, right? So just wait. Okay, now you see this is the magnetostatic energy expression. Okay, this is electrostatic, this is magnetostatic. Now if you combine these two, then you're gonna get electromagnetic energy, right? Combining these two, we get this term. Okay, and here we have differential coefficient with respect to time t. That means this is rate of change of electromagnetic energy, right? So hope you have understood this. Okay, so now what does this term represent? This one. Okay, so let me go back to a new slide. Okay, so here you see the first term on right hand side. This is the first term on right hand side. Is this represents energy flows out per unit time through the surface S, which bounds the volume V. Okay, and this E cross this term here you see this this E cross H, this is nothing but Poynting vector. Okay, and this second term on the right hand side of this equation equation number 7, this equation here you see, this is the second term. So this is this right hand side, a second term on the right hand side, that is volume integral E dot z vector d tau. This is nothing but rate of doing work, or you can say power. Let me explain how. We know that power P can be written as dot product of force into velocity, and the force so just wait, the force experienced by a charge q moving with velocity v is given by F is equal to q into E plus V cross B, which is also known as Lorentz force, right? So if that is the case, then this power P can be written as q into E plus V cross B dot V vector, which also can be written as E dot V plus V cross B dot V, and there is a vector identity. This, according to that, this must be 0. If these two are same vectors, so this must be equal to 0. So if that is the case, then power P is equal to, we get E dot V, q into E dot V. Now you see, let me go to next slide. Okay, you see this expression of power or rate of doing work for continuous charge distribution, for continuous charge distribution in a volume, and density. Charge density we have already mentioned rho, and we have considered, suppose this is volume V bounded by a surface S, this is the volume D, and if we have considered very small volume element d tau, and volume density is suppose rho here, then the power or rate of doing work means change of rate of change of energy through this volume. Okay, that will be given by, you see, P is equal to, right, P is equal to, that can be written as rho E dot V, instead of charge q, for if we have continuous charge distribution of charge density rho, then q can be written as E dot d tau in this small volume region, right? This is charge density, because you see charge density is equal to q by volume element d tau, so that's why q must be equal to rho into d tau, right? So that's what we can write. So instead of q, we can write rho into d tau, and for the entire volume V, we can write here volume integration del V d tau. So hope you have understood this. And this charge density into this volume, that's going to give you the current density, right? That's going to give you the current density E dot J. This is going to give you the current density J. So where this current density J is equal to rho, this is rho into V. So hope you have understood this. Okay, so this is the power, and this is the second term. Okay, this is the second term which is on the right hand side of this equation. You can see this is the second term, this is the second term on the right of equation number 7. So hope you have understood this meaning of each and every term in this equation, right? So now you see, and the physical significance of this Poynting vector, right? This Poynting vector, physical significance of this Poynting vector, let me write here. Poynting vector so let me represent it by S, which is nothing but E cross H vector. Also it can be written as 1 by epsilon naught E cross B. You can write this way. So its magnitude is equal to nothing but energy passing per unit area per unit time. This is the physical significance of the Poynting vector, right? So, or you can say energy flux, or you can say energy flux. Okay, so hope you have understood this, right? So thank you for watching. See you in the next video.